give some light on the introduction of matrices and what actually are the determinants. Along with that, we will discuss the importance of determinants and the usage and the real life applications of the determinants. So, according to Galileo, mathematics is the language in which God has written this universe. So, going to the next slide. So, what is a matrix? So, the rectangular arrangement of rows and columns is called a matrix. So, what are rows and columns? The horizontal lines are called rows and the vertical lines are called columns. So, what is a square matrix actually? So a matrix whose number of rows is equal to the number of columns is called a square matrix. It is generally called a matrix of n by n order. So moving on to the next slide, we will see a determinant. Determinants are the values which are the associated part of a matrix. Let's suppose you all are the students and you have a unique roll number IDs associated with your names. Let's suppose Rohan. Rohan has the ID of let's suppose serial number. He has the serial number of 20. So it is the 20 is the number which is associated with Rohan. So determinants are actually these things. These are the numbers that are associated to a matrix. We have a matrix. Let's suppose in this picture we have a matrix 1 0 0 0 1 0 and 0 0 1. Let's suppose the number associated with this matrix is 5. So we can say that the 5 is the determinant of this matrix. We will see how we can calculate the determinant of a matrix. But before that, we have the actually the symbol on how to denote the determinants. We can write the symbol as this, and along with that we have we can write a matrix 1 0 0 0 1 0 and 0 0 1. So it is the basic representation of a determinant, and we can also write determinant as the determinant of A, and also we can denote it with a delta sign. So it is this symbolic representation of determinant. So there is a limitation for the determinants, that determinants are valid only for the square matrices. We have discussed what is a square matrix. Matrix who is of order n by n. I mean to say that it has an equal number of rows and equal number of columns. So singular and non-singular matrix concept. If we have the determinant of a matrix equal to 0, I mean if the number associated with a matrix is equal to 0, then we can say that it is a singular matrix. But if the number associated with the matrix is not equal to 0, let's suppose we can say that the number associated with the matrix is 5, 4, 3 or etc. Then we can say that it is a non-singular matrix. So find the determinant of a matrix. The matrix, we have this matrix. So first we will see that can we calculate actually the matrix of this, the determinant of this matrix or not. So yes, we can calculate. It has the equal number of rows and columns, 3 by 3 matrix. So we will calculate the matrix, the determinant of this matrix. Let's suppose we can say that this matrix is equal to A. We have denoted this matrix with A. Now, in the 3 by 3 matrix, we have to expand a matrix through some rows or columns. So we can say that we are expanding this matrix by row 1, which is R1. So we can write that expanding by R1. So how to calculate actually this matrix? So if we are dealing with this row, so we have to cut this part, the row part of the number and the column part of the matrix. So what we get as this matrix. right? So we can say that 5, 6, 8, 9 is the matrix part. Now, we are dealing with 2. So we have 2 here, multiplying by the matrix. So we will delete this row and this column, because 2 is the part of the second column. So we will be deleting the column which has 2. So the matrix remaining is 4, this 6, the 7 and 9. Now we have this number. We have the 3 numbers, so we will delete the 3 part. And I will tell that in later. So we have the 3 part now. So we will write here 3, and now we will delete this row and delete this column. So the column, the matrix remaining is that 4, 5, 7, 8. Now we have a very general concept of about 3 by 3 matrix, that it has minus in the plus in the first, minus in the second, and plus in the last. No, it is wrong. Can anyone tell that how can we calculate that? Okay, so actually we have the concept of Mij. We have to calculate the sign of the sign which we will be which we will add or subtract. The sign will be calculated through this thing, right? 1i plus j. So we have expanded that through our first row. So according to the first row, it is a11, it is a12, and it is a13. So the sign we will be representing here is 1 plus 1 is equal to 2. So 2 is an even number, so we will represent a sign plus here. Now it is a12, which is equal to 3. So 3 is an odd number, so we will represent minus sign here. a13, it is 4, which is also an even number, so we will put 4 here. But what if I will expand this through the second column? I can say you that please calculate the determinant to expand the matrix by second column. So then we have here a12, a22, a23. In this case we have 3 here. So at the first, if we will expand through this column, so at that time we have minus sign here, a22 plus sign here, and a23 again minus sign here. But we are expanding right now with the first row, so we will go with it. So now we have a first matrix 5, 6, 8, 9. So we will the simple way to calculate the matrix is multiply these numbers and multiply this number and put a subtraction sign between that. So we have a matrix 5 times.
You get this subsequently? Right now.
Yes.
Exactly.
So let's suppose we have a matrix 5, 6 and 8, 9. So what we will do, that we have 1 here along with that, multiplying with that. So 1 will be the same, 5 is multiplying with 9, and 6 is multiplying by 8. And we have a minus sign here, always it will be minus. Next we have a minus sign here, so we will put minus sign here, and the next matrix is multiplying by 2. So we will write 2 here and the next matrix. It means we will multiply 4 by 9. We will put a minus sign here, and then 6 by 7. After that we have a plus sign here, so we will put the plus sign here, and we have 3 to multiply. multiply by 5, 5 multiply by 9, 45. 8 6 are
48. 26. 42. 32.
So we will get this after this multiplication, right? So we have minus 3 multiplying 1, minus 2 multiplying by 4 6, and 3 minus 6, and 3 multiplying by minus 3. So here we will get minus 3, minus plus 2 6 are 12, and plus minus 9. So which is equal to 0. So we can say that the matrix this matrix is a singular matrix because the answer is equal to 0. Now we have the matrix of order 2 by 2, and we can calculate it by the same way. Let me open the smart code again. The question on the slide is a little bit different, but I'm writing a little bit different here. Let's suppose we have 6, 1, 2, and 3. This is the matrix of order 2 by 2. So we can simply multiply 6 by 3 and 2 by 1, and we can put a minus sign between them. So 6, 3 minus 2 by multiply by 2 minus 6 is 18. So we have the 16, which is not equal to 0. So this is a non-singular matrix. Now I have a question. We have seen the matrix of order 3 by 3 and 2 by 2. And now 1 is also, I think, a square matrix, and we can calculate the determinant of a square matrix. So what is the square matrix? What is the determinant of the matrix 2? Can anyone tell that? What is the matrix of what is the determinant of this matrix? 2.
You will get a calculator.
So we have gift for you. So it is a right answer actually. So now we have made this simple. We have made a program to calculate this with some basic steps. So I will request Danish to please come up and tell us about the program. So here we go.
Okay, so Assalamualaikum, I'm Danish. So being a student of computer science, I wrote a simple program to calculate the determinant of a 1 by 1, a 2 by 2, and a 3 by 3 matrix. So I don't think I need to explain. I have made functions to get the values into the matrices and to print the matrices, and then there is computation, and there is main function. Let's run. Okay. So first of all, we can select between a 1 by 1, a 2 by 2, and a 3 by 3. Let's start simple. We will do 1 and enter. So we will enter the array elements as it's a 1 by 1 matrix. So we only need to enter one value. So let's do 2. Enter. So your matrix is, I'm sorry if it's too small. Press any key to continue. I will press enter, so it will just tell us the determinant is true. And as it is not 0, so the matrix is not singular, it's non-singular. Okay, so wait. Rerun the program. Okay, so we will do the 2 by 2 in the end. Let's do a little tricky one to actually prove that Siddiqui calculated the right value. Row 1, you know that? Yes. 1, 2, 3. Row 2, 4, 5, 6. 7, 8, 9, press enter, so it will tell us that this is our matrix, exactly same as Saad Siddiqui's. Press any key. Okay, so step 1, as Saad Siddiqui explained, first value will be kept outside, then rest of the matrix will be here. Then as Saad Siddiqui explained why this sign is negative, so we are actually calculating the determinant by the first row, -2, and then the rest of the matrix 4, 6, 7, 9, and then the third element of the first row 3 outside, and then the rest of the matrix 4, 5, 7, 8. Next, it will take the form as Saad Siddiqui did in the smart code, 1, 5 into 9, minus 6 into 8, and same for the other values. We will press enter, and so we come, step 3 will show what's the result of this multiplication and subtraction. We get this. Moving forward, step 4, we will open the brackets, and finally our answer is 0 as calculated by Saad Siddiqui, which proves he can actually calculate determinants. Okay.
Use this matrix.
What's it?
It's a singular matrix.
Yes, sir. As the determinant is 0, so the program also tells that the matrix is singular.
You people made this program by yourself, or you copy it?
I did it myself, sir.
Okay, clapping.
Do I also need to do for 2 by 2 matrix? If you Okay, thank you very much. Okay, now I will hand over the rest of the presentation to my friend Mahad. So give him a round of applause.
Please, we have very short time, please. That's okay, just carry on. Time skip okay, this is some kind of,
Okay, I want to make one thing clear, that if we ask you a question and if anyone is able to answer that, so as we give a chocolate to Rohan, so everyone has a treat if you are able to answer the question.
Thank you so much.
Again.
Then it counts for you as well if you answer the question.
Thank you so much. Sure.
So the determinant of a matrix can also be found by converting the matrix into a row echelon form. तो एक तो बेसिक मेथड था जो साद ने बता दिया था, लेकिन एक और मेथड भी है कि मैट्रिक्स को जो है वो अगर रो एचेलॉन फॉर्म में कन्वर्ट कर दें तो उसके थ्रू भी जो डिटरमिनेंट है वो फाइंड हो सकता है. फॉर एग्जांपल ये 1, 2, 3 और -2, 4, 6, -4, 2 और 6. तो अब इसको रो एचेलॉन फॉर्म में कन्वर्ट करने के लिए ये जो 3 डायगोनल के नीचे लेटर्स हैं और डिजिट्स हैं, इसको जो है हमें 0 करना पड़ेगा. तो फॉर दैट उसके लिए पहले हम जो है इसको मल्टीप्लाई करेंगे -2 यहाँ से. तो 2r1 प्लस r2 और 4r1 प्लस r3. तो ये हो जाएगा 1, 2, 3, 0 और ये 2 और 4.
It's better you should portray using the program. Don't do it manually.
Programs?
Yes,
Okay.
Thank you, Mahad. Clapping for Mahad.
Thank you so much.
Okay, so we made this program which will allow us to convert a matrix into row echelon, and then we'll calculate the determinant with that. Okay, let's use the same matrix that Mahad wrote.
But that's okay, leave it. Maybe Yasin can use it.
1, 2, and 3, and I also put a constant value, but right now there is no constant, so we'll keep it as 0. -4. Okay, so this is the formula which we would have if we put all of these values 1x plus 2y and whatsoever, and this is the matrix. So if I just continue, first we will reduce the first row, meaning to make this number 1, we will divide the number by itself, and then we will divide with all of the numbers.
You copied this program or you?
I made it myself.
Huh?
I made it myself.
Oh wow. Okay, you can conclude it. I think it's very good because computation is such a thing which can give us.
And then in the ending, you will also get the values of x, y, and z, and as well as the determinants equal to 20.
Wow, brilliant. Excellent. Well, yes.
So,
as
No, chocolate.
So as my fellows explained that what is matrix and how to calculate determinants through many different various ways. But my question still remains, what is determinant? In real life, where is determinant? Or in space, how can we even define determinant? So let us talk about it. Suppose we have a matrix, let's say 2, 0, 3, 0. I'm doing it in a system consisting of only 2 linear equations because the whole board is I guess 2D plane, so I have to stick with it. Also, I guess you all have, I'm sure about it that you all know about that if a matrix is presented in this form, it's basically like it represents this kind of thing, like this some kind of x, this is y, and so on. So let's say every matrix in a space has some kind of a dimension. So for that dimension, we use one vector named I hat, and the other vector in this case will remain j hat. And if obviously if the matrix is in a space or a 3D, then there will be another unit which will be called z hat. And these are just dimensions, you can call them whatever you want. Okay. So let me draw a quadrant. I'm not going to compute how like this determinant can be formed. Let me give you a very simple example. Let us consider 2, 3. Oh sorry, there's a 0 and there's 2, a 0. The first value, as I told you earlier, x, y, it represents x. It means add x 2 and y 0. There's a point. Second value, it represents 0, 3. Add x 0, y 3. Now this thing, this one, the first, because it's the first column, it represents the I hat. The second column represents the j hat. And let us say that they both occupying a space which is, you can say 2 into 3, like it's determinant. What is its determinant? Anyone? 6. So if you calculate this area will be 6. Now, why do I even use this kind of a linear transformation? Like, but linear transform, I am talking about linear transformation, how a vector, if it is represented in a quadrant with a block of 1a, let's suppose at the first it was 1a, and then after linear transformation, it scales up to 6a.
This determinant is 6 or minus 6?
6. So 2 into 3 is 0. It's a simple one. So, like, why I am talking about the linear transformation? Because it just scales the matrix. Let us consider another example. You can say 1, 1, 1, 0. Now, in this case, what will be the determinant? Anyone? 1. But this is just the computation. Let's talk on the quadrants. As I told you, 1, 0. This is our I hat. 1, 0. It stands at x1, y0. Yes. This is I hat. This is 1, 1. It means at x1 and I1. Here's the point. And here, at this we combine them. So this is our dimension of the matrix which is written here. At the start, the quadrant was like this. Like it was just occupying only one volume of the space. But after the transformation, it's all of its dimension in the quadrant changes according to the linear transformation. This special scaling property of change in any area of the matrix is called determinant. This is determinant in space. Now you have seen how it scales. Like here it does not scale, it just changes its position. So it's more like a translate into the space using its own dimensions. Now let us say we have another matrix having 0.5, let's go into 5, 0.5, same value. Its determinant would be 0.5. Yes. So if we represent this matrix in plane, let's say at the start the matrix was covering only one block of the quadrant. After this transformation, by making these points, its value shrinks to 0.5 of the original matrix. This is called determinant. Now, you all will be wondering that we are just talking about the singular matrices. What happens if a matrix becomes non-singular matrix? What happens if it becomes singular? Let me ask one question. What is the determinant of a zero matrix? Zero. It's a quite general one. Now, my question is this, Saad, away from you. My question is this: where its point lies in the plane?
Origin.
At the origin. Saad, still question from you. Its determinant is 0. Yes. I guess you got all the computation, you can do it in your own mind. Its determinant is 0. Where its point lies in the plane? Still. No.
Give us chocolate back.
Why? Let me tell you why. There is a reason behind it. As I told you, just split the matrix into this form. We have 2, 4, 2 and 2, 1. This 1, 2, 1. Let's create an I hat of this. It means 1, 2, 3, 4 at the point 4 and 1, 2. There. There's I. This is I hat. This is 2, 1. 1, 2 and 1 here. This matrix is singular. The reason is because of both the point lies on the same plane. This is a collinear. Like you cannot say the J hat is there, the I hat is there. What's the area? Which is approximately 0. This is the reason that we cannot just say that a matrix having entries and its determinant is 0. How can we say it lies on the origin? It's not possible. So the main reason behind it, why it's singular or why its answer determinant is 0, is the thing is it lies on the same plane.
Exactly.
Now let us talk about the inverse of the matrix. As we are in the plane, we also have seen that how a matrix inverse, we can find the inverse of a matrix, but how this inverse. Here goes your I, and there is your J. Sorry, by the way, my ordering about this. So now here the difference is, you can see the difference that here's the I is on the left side from the J. So you can say the whole plane just inverse. Now if you invert, this is what caused the A inverse of matrix actually in the plane. How its dimension rotates. And for that reason I have also made a program in the 3D animations. Let's run it.
That's okay. Pretty good.
As you can see, let's suppose this is a plane where the I is here.
That's okay.
The I is here and the J is this one. I is on the right side from the J. But after the inversion, what will happen? In actual, the whole plane just inverts. Here's the determinant 0 and here's it just inverts, and J will become at on the right side and I will be at the top.
Exactly.
So,
kind of imaginary work. Okay.
yes, this kind of thing. Its applications are used mostly in the making of the game design, where we use the image inversion of the original image to invert it, and then this kind of like animation we can put it there. As it's just a simple program.
Okay, where do we use the determinants? If we want to find the inverse of a matrix, we use determinants. So if there's a singular matrix, will it have a determinant? Will it have an inverse if the determinant is 0?
No. That's okay. After this, okay, you can. No,
that we can throw it.
Next time you feel bad feeling the exam.
Okay. I'm sorry. This is a bypass. Yes, please.
We can also use it in Cramer's rule, which will tell us the values of x and y, and also we use determinants for that purpose, and we can also find the area of a triangle for these determinants. So if we take this one, this will be 6 minus 6. So it will be 0, so we cannot, there's no inverse of this. If we use this one, it will be 7 minus 6, which is 1. It will have an inverse, and should I calculate?
No. That's pretty good. You're smart.
Mahad will explain Kramer.
Oh, yes, please, Mahad.
We can also find the determinant using the timer rule. I would not solve it because of shortage of time. So we will just do that 3. मैं just explain करूँगा कि 3 minus 2 4 और यहाँ minus 1 होगा. पहले एक normal उसका determinant लेंगे और उसको मैं for example a determinant कह देता हूँ. और फिर ax determinant के लिए हम ये करेंगे कि -4 3 -2 और ये -1 हो जाएगा. फिर इसका determinant लेंगे, इसको मैं ax determinant कह देता हूँ. और फिर इसी तरह y के लिए अब हम इस -4 -3 को इधर शिफ्ट करके तो उसका एक y determinant होगा. और फिर फाइनल स्टेप उसको कैलकुलेट करने के लिए ये होगा कि ax determinant over a determinant, तो इससे x की वैल्यू आ जाएगी, और ay determinant over a determinant, उससे y की वैल्यू आ जाएगी. अभी टाइम नहीं था तो इसलिए मैं सॉल्व किया.
Question. My whole team is here, so we are open for the questions.
Yes, thank you so much. Question, please ask question. That's all.
Sir, is it possible without using bracket we represent a matrix?
We have to represent a matrix by our modulus type brackets. So
why are we not using this slide?
Okay, thank you so much.
That's representation of matrices of the linear equations. So that's why we just combine them in the
Look, you are genius. You know it is a matrix, so we did.
That's okay. That's okay. Pretty good. All are brilliant. Thank you so much for asking.
Any other questions?
Okay, you need to give chocolate after the class. Okay. Next question, please. Okay, my question, please. From Suleman and your team, you said that once a matrix kind of a singular, it is having the same, you can say, localization point. In this case, it will not cover any area. For example, a moment ago you portrayed some example that both of I and j will at same point due to collinear concept. So please could you explain it?
Sir, the reason is it will not occupy any kind of area in that plane. Like we cannot just say if the matrix having an entry is just like this 4 2 2 1. We can just say it lies on the origin because its determinant is 0.
Okay, you want to speak up, please. You want to say that whenever we are getting determinants, it is telling us some kind of net information.
Sir, it's giving us the area or the linear transformation of a matrix in the plane. That how a matrix actually occupies its area in a vector space or in a plane. Sorry, by the way, this is we did it in a 2D dimension because I cannot do the third dimension. This thing.
That's okay, pretty good.